dementia researcher with a blog and a rating.
MEGry Christmas to all. Snow is falling softly outside, lights twinkling in the dim morning light as you rush downstairs to find a large box under the Christmas tree. It sits expertly wrapped in red paper with a large golden bow adorning the top, and most excitingly of all, when you look at the label, it has your name on it. You're about to tear into the best gift you've received since that epic pair of socks 2 years ago when a judgmental cough sounds from behind you. And it is at this point that you're reminded, no opening presents until everyone else arrives. You look down at the box and then up at the clock. If only you could find a way to look inside without actually having to open it. If only you could know what's going on in there, whilst leaving that bow pristine on top. Trying to understand the inner workings of a system we can't directly observe has always been a challenge in neuroscience. Though we can measure straight from the brain, most of our methods rely on sensors outside the scalp detecting signals to determine the mechanisms at work within. Magnetoencephalography, or MEG, is one such method. MEG measures the magnetic activity produced by clusters of neurons firing together. It does this using superconducting quantum interference devices, or SQUIDs, perhaps my favourite acronym in all of neuroscience. The magnetic fields produced by the brain are understandably very small, and so the MEG scanner is housed in a magnetically shielded room to reduce the impact of external magnetic fields, such as from the Earth itself. We also use electrodes to help screen out sources of other biological magnetic activity, such as muscle movements and eye blinks. Though small, these magnetic signals aren't distorted by travelling through the skull, unlike the electrical activity measured by EEG. MEG therefore has a higher spatial resolution, as fewer neurons need to fire in synchrony to be detected by the sensors. With all that in mind, MEG scanners can provide a rather unique insight into the brain, with better temporal resolution than an fMRI, but better spatial resolution than an EEG. Fantastic! Forget whatever is currently under the tree, I want an MEG scanner for Christmas, right? Unfortunately, Santa may not be popping down your chimney with a brand new MEG for a few reasons. The first is that, like many brain scanners, they're incredibly expensive. Even with all the elves working overtime, I'm not quite sure Santa can swing a brain scanner that costs between £1 to £2 million. Another problem is that your festive deluxe MEG scanner is a bit like a remote-controlled car that comes without batteries, i.e. useless without popping to the shops again first. Without a magnetically shielded room, current MEG scanners somewhat fall apart, leaving us with a lot more noise and a lot less signal than those millions are worth. Finally, even once you're all set up, not everyone can play with your fun new Christmas present. People unable to sit still for long periods of time may particularly struggle, and it's very difficult to run naturalistic experiments when you can't really move your head. This is why EEG remains so popular in areas like developmental psychology and the study of sleep. The system is also reliant on participants being able to come into a research unit. As someone who works regularly with dementia patients, some of whom have mobility issues, home visits aren't a luxury, but a necessity if we want to make our research more inclusive and accessible. There's some research you simply can't do with a stationary scanner that requires its participants to stay just as still. And this has been the state of the art in MEG for a few years now. Every type of brain scanner has its drawbacks, and as long as you understand that and take the necessary steps to reduce their impact on data quality, then all is relatively well. However, in a recent visit to MEG UKI, a national conference focused on the latest advances in MEG research, I discovered that Santa's helpers, aka in groups of incredibly hard-working researchers across the globe, had been working hard on something new this festive season: optically pumped magnetometers, or OPMs. OPMs are an alternative to our dearly beloved SQUIDs I mentioned earlier. Instead of requiring a fixed array of sensors which are super cool to an Arctic minus 269 degrees Celsius, OPMs are self-contained units that are about the size of a Lego brick. Using specialized helmets which can be adapted to suit different head shapes, these sensors can be placed just millimeters from the head, allowing us to get much closer to the brain than with our traditional MEG setup. Theoretically, this should allow for improved sensitivity to neural signals, but for now they remain comparable to our SQUIDs. The clear advantage to these smaller self-contained systems is that they can move with the head itself, bypassing one of the main limitations of current MEG. In a brilliant demonstration of this new portability, researchers at MEGUKI showed how they had taken their OPM system in a suitcase to another country, where they had it ready to begin scanning in only 30 minutes. Santa may still not be bringing you a MEG scanner for Christmas, but at least now it would fit on the sleigh. And finally, though they currently need to stay in their shielded room, the same research group suggested that this might not be the way for long, as they experiment with lowering this shielding in OPM setups. The brain has always been a bit of a black box, with advancing methods constantly improving our ability to look inside without the need for invasive surgeries. The trade-off between high-quality data and accessibility has always been at the forefront of neuroimaging, but could it be that OPMs will reduce the need to choose? The sensitivity of an MEG with the portability of an EEG could certainly make for an exciting present in the years to come. And so I'll exclaim before I cease to write, MEGry Christmas to all, and to all a good night. For more work exploring OPMs, try Brooks et al. 2022, Magnetoencephalography with optically pumped magnetometers, the next generation of functional neuroimaging.
Thank you for listening. Join the Dementia Research bloggers and share your own views.